So, we are in the 7th week of our talks, of our lecture. So, we are almost running towards the end of our session with calculus. So, more we are going to learn about applicability in these few sections, and then 1 or 2 lectures, and then we go on to the more deeper ideas. As I said, that I would like at least some students here to jump from calculus to real analysis, those who would do it, because these are the strengths one needs to gain. Specifically, your knowledge of real analysis or advanced calculus would be extremely important when you are going to study engineering, when you are going to study economics, when you are going to study physics. So, here we keep on our applications of definite integral. This is I think the 3rd lecture, if I am not wrong. So, here if I recall what I did in the last class, at the very end we were telling that if there is a curve and the curve is described parametrically, every point has a coordinate x y, and it is described parametrically in the following form, where t is restricted from B to A or something, it could be no restrictions at all. Now, the length of the curve, is actually given as an integral from A to B root over f dash t whole square plus g dash t whole square. This is what we had also tried to prove. So, our aim here is now to show you some applications, how to actually use this, whether by using this we get results which you already know. So, that verifies the usefulness of this formula. So, first you have to start with the most simple object of all, but the most intriguing object of all, the circle. So, the circumference of a circle. So, let us try to draw the circumference of a circle. So, here is a circle. Say radius r1, whatever you want to say it is of radius r. So, how can you write? Every x can be written as cos t, y can be written as sin t, or rather I am taking this to be of radius 1. So, I am taking a circle of radius just 1, x square plus y square is equal to 1. So, if you take it, and t of course varies from either pi to minus pi or 0 to 2 pi, whichever way you want. So, any point here on the unit circle with 0 0 as a center can be written as cos t sin t. What is this t? T is actually representing this angle that you get when you join it with the point, because here if you drop the perpendicular, this is your x coordinate and this is the radius, the hypotenuse of this right angle triangle. So, this by the radius, this distance by the radius, so x by the radius is a cos of t. So, x equal to r cos t. So, if it is x square plus y square equal to r square, then the parameterization is x equal to r cos t and y is equal to r sin t, right. So, ultimately, so if you add up and if you square and add, you will get this. So, how do I compute the circumference of this? So, compute the circumference of this, you now have to use the same formula. I am just doing in this particular situation, this case 1, for r you can know what is the answer. So, 0 to 2 pi root over, this I call as f t. So, f dash t whole square plus g dash t whole square dt. Now, if I look at this situation, what is my f dash t? So, in this particular case, my f t is equal to cos of t and g t is equal to sin of t. So, here f dash t is equal to minus sin of t and g dash t is equal to cos of t. So, what do you get? So, here you will get 0 to 2 pi root over minus sin t square plus cos t square dt, and that will become 0 to 2 pi root over sin square t plus cos square t dt. Sin square t plus cos square t is 1 and the root of 1 is 1. So, this is equal to 0 to 2 pi dt, which is finally 2 pi. Now, if there was an r here, that r would remain here, it will come here and this will become r square into sin square t plus cos square t. So, root over r square will just give you r. So, it will become r into 2 pi. So, 2 pi r, which the formula which you are so familiar with. So, when the radius is 1, the length is nothing but 2 of pi. So, if you put also minus pi to plus pi, then also you will have the same answer. Then also you will have pi minus pi, you will get 2 pi. So, another example from, we will take an example from the famous book Thomas's calculus. I just want to again reassert that we are using Thomas's calculus. So, G.B. Thomas was a very famous teaching professor at the Massachusetts Institute of Technology in the US, and he was so famous because of his text that when he died, his death was announced on the first page of the New York Times. So, you see a great teacher also has a great value to a society. And writing a book like Thomas and Finney, like when I was a young undergraduate student, then we had this book Thomas and Finney, Calculus and Analytic Geometry, but Thomas has died after that. Now you have Thomas's calculus, which basically means the same book, but some other people are adding on to it and doing the stuff. So, it is just, you just Google it, you have their authors keep on changing. So, this book is one of the most important book in the history of modern calculus teaching, modern calculus education. It has so many things inside it, lot of things to learn and good fun problems to work on. So, now we will look at a curve which is called an asteroid, and it is parametrically given as x equal to cos cube t and y is equal to sin cube t. Okay. So, so let us look at this curve. It looks like this. and these endpoints you can very well understand, these are nothing but the x axis is a plus 1 point, minus 1 point on the x axis, plus 1 point on the y axis, minus 1 point on the x axis. This curve called an asteroid has the following representation: x equal to cos cube t and y equal to sin cube t, with t lying between 0 to 2 pi. So, you have cubed it, you have maintained the same story like the circle with cos and sin as the component function, and then you have cubed it. Now, I want to find the length of this curve. So, should I bother about finding the length of this whole curve? I would rather first concentrate on I will be bothered about finding the length of this curve, because you know there is a symmetry in the diagram. So, once I know the length of this curve, all of these curves or parts are of equal length, I just have to multiply by 4. So, what I want to do is just I want to figure out the length only in the first part. I am not going to figure out the length in the other part. So, let me just first find out what is f t is equal to cos cube t, g t is equal to sin cube t. So, what is the, so it is 3 cos square t and then derivative of cos t, which is minus sin t. Here it is 3 sin square t and into the derivative of sin t, which is cosine of t, and that is it. Now, if you take the square of these, so sorry, I am making a mistake. So, here I am having f dash t is this and g dash t is this, not this is not there, this is a function. So, you will have f dash t whole square is equal to 9 cos 4 t sin square t, and g dash t whole square is equal to 9 sin 4 t cos square t. So, my length, which I just only want to find from where the angle is in the first part, but the angle varies from 0 to pi by 2. So, 0 to pi by 2, that is 90 degrees, then I will have root over 9 cos 4 t sin, cos 4 t sin square t plus 9 sin 4 t cos square t. So, that is equal to 0 to pi by 2 root over 9 times cos square t sin square t into cos square t plus sin square t. So, what I will have L is equal to 0 to pi by 2 root over 9 cos square t sin square t. So, if I take the limit out, because cos t into sin t is positive, I will have 0 to pi by 2 3 cos t sin t dt. So, this can be replaced by 3 0 to pi by 2. Sometimes your mind wanders because you think as you are teaching also. So, this is cos sin 2t, sin 2t is equal to 2 cos t sin t. So, it is sin 2t by 2 dt. And then of course, I leave in to you to find the answer, which is nothing but 3 by 2 at the end. So, this will be this. So, when I put 0, that cos 2, it will become 0, it will become 1, and it will become t equal to pi by 2, it will become minus cos of pi. So, 3 by, so there will be 3 by 4th of course. So, cos of pi is minus 1, so it is 1. So, it is 3 by 4th cos of, because cos 2t by 2, 2 has come out, 3 by 4th, so it is 1 minus plus cos 0 is 1, it is 2. So, it is 3 by 4th into 2, which is equal to 3 by 2. So, 3 by 2 is the answer for this part only. So, for the length of the whole curve, so total length TL, total length is 4 into 3 by 2, which is 6 units, whatever units you want. So, I want to now find the length of a curve given by the function y equal to fx. I have not told you anything about the parametric representation. How can then this idea be used there? So, that is a important issue. So, let us have a curve y equal to fx, which is continuously differentiable, derivative is very nice, and then how would you try to find the equation of such a curve using the ideas that we already have built up here. So, let us see what we can do there. My problem would be that I am given a smooth curve y equal to fx. Smooth curve means that it has a derivative, is smooth, means the derivative is continuous. This implies dy dx is a continuous map, continuous function. So, now find the length of this curve, say from 2 points A to B. So, it is defined say between A to B. So, you find the length of this curve between A to B. I am trying to tell you now that okay, this is my y equal to fx between A and B, and you try to find the length of this by whatever knowledge you have gained in finding the lengths of parametric curves. So, now how do I parameterize this curve? So, what I do, I put x equal to t and y itself as f of t. But t of course has to vary between A and B, because the t is same as x varies between A and B. So, now you can ask me what about the derivatives at this point. One could be that the function is also known over the whole R. So, the derivatives are there at A and B and they are continuous. One could be that I take the derivative at the end points to be only derivatives in the right hand derivative sense and left hand derivative sense, and right hand derivative sense when you come to A, and when left hand derivative sense when you go to B, and as a functions in that state these are continuous. You can look at it in either way. Okay. Now, so here what would one do? That is very interesting and important. The fact that we have now parameterized like this, my length is nothing but integral a to b root over. So, this is my say phi t and this is my psi t. So, I will have phi t dash whole square plus psi dash t whole square, but then dt, then a to b root over what is phi dash t? Phi dash t is 1. What is psi dash t? Psi dash t is f dash t whole square. So, what is dy? So, basically df dt or rather dy dt. Dy dt is dy dx into dx dt. So, dx dt is 1. So, dy dx is equal to dx dt, because dx dt is because x is same as the function phi basically. So, dx dt is just 1. So, it is nothing but, so this is nothing but dy dx. So, what I get is integral a to b root over. So, here I have to use a chain rule, please observe this, 1 plus dy dx whole square. So, how simply we obtain, once we have that knowledge, we obtain this very simply. There is another way of looking at this curve, the length is that okay, you take a very small elemental part here, these are called elemental part in calculus, and call this length to be d of s, where s is the curve, right, or d of L, whatever you want to say, d of L say, right, of the length, or s is arc, so small arc, so s is a typical symbol of an arc, so ds. So, assume that is almost straight. So, basically, so now this point is some xy, this point is some another xy. So, this is the change in x. So, basically what you are having, if you magnify this, so here is your x and here is a y, the same thing we did yesterday. So, change in x and change in y, we are approximating this length del x and del y. So, we are approximating, we are writing that ds square when s is very very small is almost same as or rather I should write del x square plus del y square. So, what is the length? Length of s. So, length is basically when you take the limits is integral a to b root over dx square whole square plus dy, the differential. I am not, obviously I have not told you exactly what the differential is, but or you can do like this. So, this is another way, if you do not know even about this standard this thing, this is another way. So, this is what you have done. So, what you do here is that del s square is root over del x square, oh sorry, root of not del s square is this, del s is, so apply the Pythagoras theorem. So, this is actually what you are actually approximating the del s or del s by this hypotenuse. So, del s is approximately this. So, del x square into 1 plus del y by del x whole square. So, you bring del s del x, you take the square out, is equal to root over, not is equal to, approximately 1 plus del y by del x whole square. But you see, as you make this smaller and smaller, as the difference becomes smaller and smaller, that is when del x and del x tends to 0, and hence del y also tends to 0, because the function is a continuous curve, because small change in x must give you a small change in y. What is happening? The curve almost approximates the straight line. So, in the limit as del x tends to 0, del s del x in the limit this two ratio, this the hypotenuse length almost approaches the actual length of the del s. So, in the limit the lengths coincide. So, basically this is now equal to, so in the limiting form they are same. So, when you are coming to the limit they are same, because you can also just do it, you can also do an epsilon delta argument in the sense that if you take del s instead of del s you take the del h, then del s minus del h, that difference could be made less than epsilon. All these argument you can do, but here we are making intuitive jumps, sometimes that is also fun. So, this is nothing but when you now what is in this limit? It says what do I get? I am rubbing this spot. So, I am rubbing this spot. So, what I am getting here? From here this side simply means ds dx, and because this function is continuous the limit can be brought into it, because root x function is continuous in the positive orthen. 1 plus some square, now any square of any number is positive. So, 1 plus when you take the limit it is nothing but dy dx whole square. So, ds is equal to root over 1 plus dy dx whole square dx. So, the total length is nothing but sum up of all the small elemental parts. So, it is a to b ds, which is your L total length. So, it is a to b or rather I should write 0 to L ds. It is not a to b, because when a x is a, the starting length is 0, and when x is b I have covered the total length 0 to L. So, I have moved from 0 to L. So, L is this and this whole square dx. So, this is how you compute the length, and that is exactly what we have done using the other ideas. So, it is the same sort of limiting ideas that is pervasive all of calculus, and that is what I really want you to show. You can now figure out any issues like that. I do not want to get into the situation where there could be a discontinuity in dy dx, because once you have discontinuities there are certain issues which need to be handled in a different way. Then you have to write y in terms of x, you have to do dx dy. So, things are slightly complicated, we will not get into that. So, you now have a brief and a clear idea how to compute it for a curve. You can try out and do some calculations yourself, taking things from the anywhere on the web. So, we end the lecture now, and then in the next lecture, the second lecture of the 7th week, so 8th week is the last week. So, we will talk about how to calculate surface areas. So, that is exactly what would be our discussion. Thank you.